Assalamualaikum. Today, me and my group members, which is Lakshita, Kashmir and Matthew, will be presenting about a machine called Hydropower and us. So what do we know about hydropower? Hydropower is one of the leading renewable energy sources in the world. It uses a kinetic and potential energy of water to generate electricity and produces much lower greenhouse gas emissions compared to a conventional power generation. In a hydroelectric power station, flowing water spins a turbine, converting water energy into a mechanical energy by a synchronous generator, this is important for a grid stability because it operates a constant speed. Inside the generator, there's a rotor and a stator. So the rotor creates a rotating magnetic field, while the stator creates an alternating current through the electromagnetic induction. So in overall, hydropower offers a clean, efficient, and sustainable way to meet today's electricity demand. I will be explaining about the IEE standard, which is IEE standard 115 and 1110. In IEE standard 115, this standard provides a guidelines covering performance, electrical, mechanical, thermal, and operational aspects to ensure that hydropower generators operate efficiently, safely, and reliably. In a performance aspect, it states that the energy conversion of a generator is the relationship of its output power to its input power. In accordance to standard methods, the parameters can be determined by direct or indirect measurements, which is including the measuring output power, efficiency, and different types of losses. In electrical aspects, from what we have searched, it explains that the standard testing procedures used to evaluate the electrical performance of hydro generators. Tests such as open circuit and short circuit tests, voltage regulation, and armature resistance measurement are carried out to understand how the generator behaves electrically. Next is IEE standard 1110. This standard focuses more on modeling and parameters determination of synchronous generators. This standard also mainly used for analysis and simulation. In a modeling aspect, it states that some guidance on how synchronous generators can be mathematically modeled for power system studies. This is to make sure that the hydropower generators has an accurate modeling. This is because a proper generator could help represent how the hydro generator during normal operation and during disturbances. Next is electrical parameters determination aspects. These aspects explains how the electrical parameters such as reactance and time constant should be obtained. So, for hydro generators, these parameters describe how the generator responds electrically when there are changes in load operating conditions. In overall, IEE standard 115 is about a practical testing of a machine, which is a real machine, while IEE standard 1110 is about a modeling generators for system studies.
For rotor eccentricity, it creates an unequal air gap, leading to asymmetrical magnetic forces and destructive vibrations. We mitigate this through online monitoring using air gap flux sensors to identify imbalances for mechanical realignment. As for field winding turn insulation faults, these are internal shorts caused by thermal aging of rotor coil insulation. These are detected using electrical testing such as recurrent surge oscillography (RSO) to pinpoint deterioration for targeted repairs like rewinding. Although synchronous generators are very robust, they have some potential faults that, if allowed to continue unchecked, may result in catastrophic failure. Two such potential faults that form critical issues within hydro generators include rotor eccentricity faults and field winding turn insulation faults.
Salient pole generators with laminated rotors are usually constructed with damper bars located in the pole face. These generators must be multipolar machines. Low rated speed generators will eliminate mechanical transmission.
For case study, to summarize the hydropower generation process in a simple way, water from the reservoir flows down to the penstocks, and the pressure of the water spins the Francis turbine. The turbine is connected to a synchronous generator, so when the turbine rotates, the generator rotor also rotates. This rotation produces AC electrical power, stable voltage and frequency. After that, the electricity is sent to a transformer to increase the voltage. Once the voltage is stepped up, the electricity can be transmitted safely and efficiently to different cities and consumers. So, that is how the hydropower converts water energy into usable electrical energy. So, hydropower synchronous generators is used in many real-world applications. First, it powers large national hydro plants like Bakun, providing stable electricity to the grid. Second, small and micro hydropower systems supply energy to rural and remote areas. Hydropower is also combined with solar and batteries in hybrid systems, such as those used in rural Borneo. Because synchronous generators help stabilize frequency, they are important for grid regulation and system stability. Lastly, many industries in remote areas like mining and timber processing use small hydropower to reduce energy costs and maintain reliable power.
For calculation part, we are required to find the power factor. Based on the article, in this specific hydropower system, the power factor is not a fixed physical constant but is programmatically controlled. By using the table above, we can use the rated parameters provided and apply the formula. Here shown how we can get the power factor.
Hydropower is highly sustainable because it uses a renewable water source, has a very low carbon footprint, operates with high efficiency and can last for many decades, while also helping stabilize the electricity grid. However, it does have environmental impacts. These include changes to ecosystems, possible emissions from reservoirs, effects on nearby communities, and changes to downstream water flow. To reduce these impacts, modern projects use mitigation methods such as fish passages, sediment management, water quality monitoring, and proper environmental planning.
In conclusion, our study of the synchronous generator within the hydroelectric sector has shown that technical excellence and sustainability must go hand in hand. By following IEEE standards, we ensure that these machines are not only efficient but also predictable and stable within the national grid. As we discussed with the Bakun Dam case study, these generators are the workhorses of our renewable energy infrastructure. However, their longevity depends on modern engineering solutions, like the online diagnostic techniques we explored, to mitigate faults before they occur. While hydropower presents environmental challenges, the use of high-efficiency synchronous generators provides a path towards zero-emission power that can last for over a century. We believe that through continued innovation and adherence to engineering standards, hydropower will continue to lead our country toward a greener future. That concludes our presentation. On behalf of Group 3, thank you for your time and attention.